Chapter 9, Section 7 in the 7th grade note-taking guide is entitled Squares and Square Roots. So this is really our last study of inverses of a number. We've studied a lot of the inverses this year. We've used a lot of the inverses this year. We've looked at how adding and subtracting are opposites of each other extensively in the process of solving an equation. And we've looked at how multiplication and division are inverses of each other. Again, done that a lot with solving equations. Here's the last set that we have to look at, squares and square roots. Squares and square roots are opposites of each other, just like those other pairs I just mentioned. To understand a square root, you want to understand a square first. And a square is something I think you already have a pretty good understanding. A square is a square of a whole number. A perfect square is a square of a whole number. So when we take the number 1 and square it, which means multiply it by itself, that result is known as a perfect square. So when I take 1 and square it, that's the same as 1 times 1, or 1. When I take 2 and square it, 2 times 2, that's going to give me 4. 3 squared, that's the same as 3 times 3, which is 9. 4 squared is the same as 4 times 4, which is 16. And I can keep going down the list if I want to, but 5 squared is going to give me 25, and 6 squared is going to give me 36, and 7 squared is going to give me 49, and 8 squared is going to give me 64, and 9 squared is going to give me 81, and 10 squared is going to give me 100, and 11 squared is going to give me 121, and 12 squared is going to give me 144. Okay, there's your squares. Now, when I read this list the other way, it's instead a list of square roots, which makes sense because I've already told you that these are inverses of each other. So as I read the list going back this way, from right to left, opposite the direction we read, then it's a list of square roots. What is a square root? It's one of the two equal factors of a number. So if I said to you, what's the square root of 16? You could come back and say, oh, well, that's 4. So there we have the idea of a square root. Now, it's not the only way I can find two numbers that multiply together to make a given number, because we could also, of course, if I'm using this example of 16 going to 4, I could also use negative 4. Think about it. Negative 4 squared. Negative 4 times negative 4. Well, as you already know, a negative and a negative, when I multiply them together, makes a positive. So when I say the square root of 16 is 4, negative 4 is also a potential solution. Now what you can see that leaves out, though, is a whole bunch of numbers like 2 and 3 and 5 and 6 and 7 and 8 and 10 and 11 and 12 and 13 and 14 and 15. Those are all things that we also have to account for, but we can't probably do those in our head. That's something that's going to require some calculation and some methods here, which we'll see here coming up. All right, back to the definitions. The final definition is that of a radical sign. That's the symbol used to represent the square root of a number. All right, so in the first question here, they're asking me to find use the model to find 12 squared, to find the square. Well, as you can see, what they did here is they laid out 12 grid boxes in terms of length and 12 grid boxes in terms of width, and then they multiplied those together. Well, when they did that, as you can see, that lays out 144 smaller grid boxes here, so 12 squared must equal 144. That's actually a logical place to go based on where we've been, because as you know, we've been doing problems where, let's say we're actually looking at a whole square, where we would do length times width, or the side length squared. Well, of course, that's absolutely me doing just that, except now I'm finally using the squared method instead of just saying length times width. Now, in the B question, I'm taking 3.5 and squaring it. Because I would have a hard time drawing 3.5 squared, or at least it would take me longer, what they do here is they go for the actual calculator method here. So on your calculator, using the x squared key with 3.5, and when you do that, you get 12.25, because 3.5 times 3.5 yields 12.25. All right, let's continue on here. you're going to see as we go through this, they're going to oscillate quite a bit back and forth between calculation and then using a calculator. When they are related to perfect squares and perfect square roots, you're going to see that they will often use a method that requires them to actually calculate on paper. When they aren't maybe perfect, they'll probably pick up the calculator more often. So number 2 here, they're asking me to use a model to find the square root of 16. Well, we're going to use the inverse of what we just saw in 1A then. We want to lay out 16 grid boxes in a pattern such that the length and the width are the same. Well, as you can see, when they do a 4x4 grid pattern there, we end up with 16 grid boxes. And because we ended up with 16 grid boxes there, that must be the square root of 16. The side length then will equal the square root of 16. Well, the side length there is 4, so the square root of 16 equals 4. Method 2 there, they're using a calculator to find the square root of 676. So the keystroke method there is to use the second and the x squared key and then typing in 676. And when you do that, you get 26 because 26 times 26 is 676. Now, one of the things you should know is you can also use a power for a square root, as odd as that may sound. You can actually use the 1/2 power to take a square root. And that might come in handy for you if you ever get a calculator that maybe has a power key but doesn't have a square root key. You can use the 1/2 power, or if you want to write it as 0.5 power, to take the square root. It actually makes sense if you think about it, because think about what we've been saying here. We've been saying that squares and square roots are opposites of each other. Well, if a square is to take the second power, the inverse here, well, the inverse of 2 would be 1/2, because when I multiply together 2 and 1/2, the result in terms of multiplication is 1, which is what that property says. So if I'm saying squares and square roots are inverses of each other, or opposites, second and 1/2 are inverses of each other as well. So it would make sense that I would be taking the 1/2 or 0.5 power to find the square root of 676. So you could do 676 to the 0.5 power, and you would also come up with 26. In that, 26 times 26 gives me 676. All right, so now in number 3 here, we get to questions where they are not using perfect square roots. And when they're not using perfect square roots, you have to use that list of perfect square roots to find what surrounds your potential solution here when they're asking me to estimate to the nearest whole number. So let me go ahead and put down that list again. Real quickly, we said that 1 squared is 1, and 2 squared is 4, and 3 squared is 9, 4 squared was 16, 5 squared was 25, 6 squared was 36, 7 squared was 49, 8 squared was 64, 9 squared was 81, 10 squared was 100. And as we said, when we read this list going from right to left, opposite the direction we read, it's a list of perfect square roots, but it leaves out a lot of numbers. What this question is asking about is one of those numbers that's left out, the square root of 40. Well, the square root of 40, well, where does 40 fall in this list? This is just a logical ordered number list. Well, 40 would fit in here, of course, between 36 and 49, which is why they're saying the square root of 40 in this first line is between the square root of 36 and the square root of 49. They're surrounding it with the perfect square roots. All right, so as we surround this with the perfect square roots here now, we're saying it's between 36 and 49. So it's between, as we read back the opposite direction, it's between 6 and 7. So if it's between 6 and 7 now, they want to know what number is it closer to, which whole number. Well, let's think about it. If I'm talking about 40, to get to 36, I'd have to go 4 jumps back. To get to 49, I'd have to go 9 jumps ahead. Well, what's closer? Well, in terms of distance, going 4 jumps is obviously closer than 9 jumps. So since 36 is closer here, all right, since it's only 4 jumps back. That's why they're saying here that it's closer to 6, because the square root of 36 here is 6, being only 4 jumps away from 40 as opposed to 9 jumps away from 40. They check this out with a calculator here. They take the square root of 40, they get 6.32. That does indeed prove to be closer to 6 than it would be to 7 based on logical rounding techniques. So indeed our solution verifies by using methods of number distance.